Okay, today we're going to talk about the equipartition of energy theorem. This is a really important idea. It applies generally, but we often talk about it in the context of gases and ideal gases. And in the Gen Chem books, and if you've taken a course in general chemistry, it's not really emphasized a lot. We come out of there really learning the ideal gas law, but this is equally important, and it's really helpful for intuition as you develop yourself as a physical chemist. So the idea is pretty simple. It says that an equal amount of energy gets distributed into all the possible degrees of freedom. Now there's a little bit of a caveat there, which I'll mention, but we won't be able to go into it deeply. But essentially, if a system has degrees of freedom, there's no one degree of freedom that's on average more special than the other, so the energy is equally distributed into those degrees of freedom. And earlier we've talked about degrees of freedom in terms of translation, rotation, and vibration. Now, this subtlety I referred to, at normal laboratory conditions, most vibrational modes are shut off to this to dumping energy in. And that's a thing that is a quantum mechanical idea, which we haven't talked about yet. We certainly will talk about it a lot in the curriculum, but here in this introductory series, we won't. So when we say degrees of freedom, we're talking about any kind of translational degree of freedom or rotational degree of freedom, and we do not consider vibrational degrees of freedom. At higher temperatures, at very high temperatures, you would do that, but in normal laboratory conditions, we only consider the translational and vibrational degrees of freedom. Now, how much energy is dumped in? Well, on a per mole basis, we get 1/2 RT, and remember R is 8.314 joules per mole times Kelvin. So that's a molar energy once we multiply by T. So to get the total internal energy, we multiply the number of degrees of freedom times 1/2 RT. So let's do a couple of examples here. Let's look at argon. So argon is a monotonic gas, so it does not have any rotations. So that formula that we talked about a number of lectures ago, 3n-5 or 3n-6, that's going to apply to a molecule. But to a single monotonic gas, there's no vibration, no rotation. So we only have the translational degrees of freedom, and we can go in the X, Y, or Z direction. And so we have 3 degrees of freedom, and our total internal energy then is given to us as 3/2 RT. Now, let's contrast that with nitrogen. Nitrogen has 3 translational degrees of freedom. That's the center of mass of the nitrogen. And then it has 2, because it's linear, has 2 rotational degrees of freedom. This one, and then coming out at you. And then this is not a rotation because nothing is moving around its center of mass. So we would have 2 rotational degrees of freedom. It does have a vibrational degree of freedom, but we do not consider that when we're at normal laboratory conditions for quantum mechanical reasons, which we won't get into. So we have a total of 5/2 RT. So maybe you could take a minute and think about, what if we had water vapor here? And we only consider rotations and translations. In that case, we would pick up another rotational degree of freedom because the water is not linear. So we'd have 3 rotational degrees of freedom. So that would be 6/2 or 3 RT for water. All right, so this is the idea of equipartition of energy. Very handy. Let's see how it's related to heat capacity. So let's consider just a gas. And one thing we didn't talk about when we learned about heat capacity yet is that the value of the heat capacity depends on the conditions under which it's measured. And the 2 most important are measuring heat capacity under constant volume or under constant pressure. And we see that those will be different. And so we want to understand why they're different. So let's get a little bit of intuition. So the definition of heat capacity is the system's ability to resist a change in temperature when we add heat energy. So we know that Q equals C delta T, right? C delta T. And so we're dumping heat in. We're looking at a temperature change. Right? If we have a larger heat capacity, then the temperature change is less. Or, to state it slightly differently, if we want to achieve the same temperature change, say 1 degree, then if we have a larger heat capacity, we're going to need more heat. Okay? So if we just take, that's the definition of heat capacity. Let's see why it matters whether we're under constant volume or constant pressure conditions. So let's put two gases in a piston here. In this case, we've got a pin holding this. So we're at fixed volume. The piston can't slide up and down. And then we're going to dump some heat in here. Let's say 10 joules of heat. Now, there's nothing the piston can do. It's just stuck there. So that heat simply goes into warming up the gas and changing its temperature. But now let's dump in that same amount of heat into a piston that's free to slide. Well, if the piston is free to slide, it can do some work on the environment. And so let's say we dump in 10 joules of heat and we do 3 joules of work. Then not all of that 10 joules has gone into heating up the gas. So the temperature change would be smaller. So here we put in, say, 10 joules. Here we put in 10 joules. We get a larger temperature change here than here. And so their heat capacities are different. And in fact, the heat capacities are such that Cp is always greater than Cv. Okay. For gases, it's a significant difference. And we'll see that in just a minute. For liquids and solids, let's think about that. For a liquid and solid, let's just put water in this piston. We dump heat in. Water does expand a little bit, but nothing like how a gas would expand. So the amount of work that the water would do would be very, very small. So when we compare these two differences, for a solid and a liquid, so for a liquid or a solid, Cv is approximately equal to Cp. Cp is just slightly bigger. So you can get away with calling heat capacity at constant volume the heat capacity at constant pressure if you're talking about a liquid, and you don't have to be super, super careful. They're almost the same. But you can't do that with gases. Gases are quite different. So let's use the equipartition of energy theorem to get the heat capacity, and then we'll see what that is for an ideal gas. So the heat capacity, the molar heat capacity, oops, this should be molar. The molar heat capacity is the derivative, the temperature derivative of the internal energy. And so we have now an expression from the equipartition of energy theorem for the molar internal energy. And so for a heat capacity, pretty simple derivative here. We haven't done calculus, so if you've done calculus, you'll see this right away. The derivative of this is we're just gonna remove the t here. That's how we would do the derivative of this linear term. Okay, if you haven't had calculus, then just take this as the result. So we get 1/2 R. So now the units are joules per Kelvin, which is a heat capacity unit, or is the same unit as heat capacity. 1/2 R per degree of freedom. So for an ideal gas, right, and this I'm just going to have to tell you, we won't work this out, but the amount of work that this will do, such that these are different, results in heat capacity at constant pressure being heat capacity at constant volume plus 1 times R. And so pretty simple formula. And then it's pretty easy then to get from the equipartition of energy theorem to the to the heat capacity at constant volume, and then heat capacity at constant pressure. So let's look at argon. Argon has a heat capacity, has 3 degrees of freedom, so we get 3/2 R for CVM. Then we add another R, so we're going to add one more R to this, so that'd be 5/2 R. So we have 3/2 R and 5/2 R for argon. In nitrogen, we have then 5/2 R, as we gotten over here, 5/2 RT, so that results in 5/2 R. Right? And then for CP, we have 7/2 R. And this is, as long as, in as much as we can treat things as an ideal gas, this will give you a very good result for the heat capacity of any gas. Just, is it monotonic? Okay, then it's going to be 3/2 R or 5/2 R, depending on whether you're CP or CV. And then nitrogen, oxygen, carbon dioxide, anything that's linear is going to be like this. And then ammonia or water water vapor, not water liquid, but water vapor is going to be, this would be 3R and then 4R. So you can impress your friends if you ask them to give you a gas, and you will tell them the heat capacity of that gas and then have them go to Google and look it up. You just got to be a little careful when you do that, to make sure that you tell them both of these, so that whichever one they find, they'll see that you were right. So you can try that. Check nitrogen, or check argon or neon or helium. Just Google the heat capacity and see that the value is 3/2 R or 5/2 R, depends on which one Google would be giving you there. All right, let's go just one step further and talk about types of relationships between pressure and volume. So we're going to make a graph here of pressure versus volume. Let me make that in blue here. And then we're going to plot the behavior of that for an ideal gas. If we are under, well, first let's define something quickly. Let's define the ratio CPM over CVM as this gamma. So for argon, 5/2 over 3/2 is just 5/3. And for nitrogen, 7/2 over 5/2 R is just 7/5. Okay, so that's our gamma. It's different depending on what these values are, as we see here with nitrogen and argon. Okay, so now let's look at an ideal gas under isothermal conditions. So we'll set the T, and then we'll look at the pressure volume behavior. So PV equals nRT, but these are all constants, so let's just set that to a constant. So then we're going to have, if I write P as a function of V here, which I have on this graph, then I'm going to have C over V, which is a behavior of hyperbola. So it's a 1 over x type behavior. That's what I've got plotted in green here. And then to change C, you just change the temperature, right? These are just fixed constants. And then if a higher temperature, we would have a bigger constant. That would be something like this. And at lower temperatures, we'd have a lower constant. That would be something like this. This behavior is called an isotherm because we're isothermal. So we can plot the isotherms, and they have the shape of a parabola, or hyperbola, so 1 over x. Well, it turns out, and we won't go into deriving this, we'll have to wait till a higher level course in our curriculum. Once we have a full course on thermodynamics, we'll see where this comes from. But we'll just pull it out here for this general course, and that is that we have a slightly different PV behavior. We have P times V to the gamma is a constant if we're under adiabatic conditions. And just as a reminder, adiabatic conditions are when heat is not being able to go in and out of the system. So the best thing to imagine here is a perfectly insulated piston that's able to change the pressure and the volume and won't allow heat in and out. That's an adiabatic system. And so Now, under these conditions, temperature does change when these go, but this is all a constant. And so for a given value of that constant, we plot what's called an adiabat. So we have adiabats and isotherms. And so this is the pressure volume behavior that an ideal gas feels for both isothermal and adiabatic conditions. And we can see that the adiabatic condition can be brought in here if we know the ratio of the heat capacities. We can get the heat capacities from the degrees of freedom, which trace all the way back here to the equipartition of energy. So, don't have a lot of homework on this. You won't see this in your book, but a good chance to just tell yourself the story of this, see if you can trace your way through and back, and really try to internalize this idea. It will be very helpful for us moving forward when we get to some of the higher level material in the later courses in this curriculum.